So good morning everyone, welcome to lecture 27. So in the last class we derived the field equations for the first law and second law of thermodynamics, and I'm just going to write them here. Okay, that's the first law of thermodynamics and corresponding field equation, and the second law is an inequality. Okay, and this is obviously in Eulerian form, and we also have the corresponding Lagrangian form. And I just want to, make slight changes in the second law of thermodynamics, write it in a slightly different way. One is to eliminate this source term, this little r, the heat energy per unit volume term, rate of heat energy per unit volume. And other is we want to introduce what is called Helmholtz free energy. So, there are several kinds of energy. One is internal energy, and let's say specific internal energy, and that we are denoting by epsilon. Then we have a specific Helmholtz energy, okay, which is epsilon minus theta times eta. You must have learned it in your chemistry classes. Then we have a specific enthalpy. That's denoted by epsilon plus PV work, isn't it? And finally, we have a specific Gibbs free energy. So there are several forms of energy which are relevant depending on what kind of process is going on. So this has epsilon plus PV minus theta eta. Okay, so here I want to write this in terms of a specific Helmholtz energy, because that is more relevant when you have thermoelastic processes going on where temperature of the system is also changing. So let me first of all, in the second law, try to eliminate this rho r by theta. So that we can do using first law. Substitute first law here. So you can see that from the first law, we have rho eta dot minus 1 by theta times rho r. No? So rho r is rho epsilon dot, then we have plus Eulerian divergence of the heat flux vector minus sigma double contraction D. Okay, so this thing inside the bracket is rho times R, which has been taken from here, okay, from the first law. And then the remaining thing, which is divergence of y dot q by theta. This is greater than or equal to 0. So this is a way to eliminate what's called R from the second law. And finally, I want to substitute the internal energy with Helmholtz free energy. So using this definition and maybe we'll call this Helmholtz free energy by psi. Okay, this is epsilon, and we'll call this psi. So psi being equal to epsilon minus theta eta, this implies psi dot is simply epsilon dot minus theta dot eta minus theta eta dot. Okay, so we can put that in here, and then we have rho times eta dot minus 1 by theta times rho times psi dot plus rho times theta dot eta plus rho times theta eta dot plus divergence of y of q minus sigma double contraction d. I hope all of you are following it. I just forgot that you guys are also listening to me. Plus divergence of y dot q by theta. Okay, and this thing we want to be greater than equal to 0. Okay, simple, substitution. And then we can see that several terms are going to cancel. Okay, for example, you notice that this term and this term, they are cancelling because there is a 1 by theta here. Also, you can expand this divergence of q by theta, and if you do that, it becomes 1 by theta times divergence of q, okay, plus gradient of 1 by theta dot with q. Yeah, this is something you can show using indicial notation also. This thing is equal to 1 by theta divergence of q minus 1 by theta square gradient of theta dot with q. Okay. Now, can you see that there is another cancellation? For example, this term, which is divergence of q divided by theta with a minus sign, that's going to cancel with this term, right? So with a positive sign. So finally, what we have is further, let us multiply by theta everywhere. Multiply by theta everywhere. The temperature. So we have minus rho psi dot minus rho theta dot eta and plus sigma double contraction d and minus 1 by theta. Please let me know if I'm making some mistake. Is that correct? So that's modified form of second law of thermodynamics. And you will see that this will be used later on in deriving restrictions on constitutive relation. So this will be used later on in deriving restrictions on constitutive relation, which is the relation between stress sigma and kinematic quantities. So let me just write down what all we have till now. So we have equations, basically all equations we have derived till now. One is mass continuity, right? According to which del rho del T plus Eulerian divergence of rho times velocity, that's equal to 0. Okay, again, please correct me if I'm making some mistake. Then we have LMB, which is divergence of sigma plus body force is equal to rho times acceleration, and which you can also write it as rho times del V del T plus gradient or Eulerian gradient of velocity times velocity. Then you have AMB, which simply says sigma equal to sigma transpose. Okay, then you have first law of thermodynamics, which we have up there. Rho times epsilon dot is equal to rho times little r minus rho r by theta. Sorry, it's divergence of q. Yeah, minus divergence of q plus stress power. And then you have second law inequality, which we derived just above. Which is minus rho psi dot minus rho theta dot into eta plus sigma double contraction d minus 1 by theta divergence of theta, sorry, gradient of theta dot with q, and that's greater than or equal to 0. Okay, so these are all the equations that we have, and the unknowns that we have here are your deformation map y hat as a function of x comma t, and of course density rho, then your sigma, and since we are using the first law of thermodynamics also, then this theta is also an unknown here, as you can see here. Theta is also a function of x and t. So these are all the equations. I mean, these are all the unknowns, which are obviously more than the equations that we have here. And that's why we need constitutive relation. Okay. Since number of unknowns are more than the equations, we need constitutive relation. Okay, which relates sigma with kinematic quantities. Okay, any questions so far? Okay. Now you see there is these are all the equations that we have, and there is no further equation that can exactly tell you the formula for sigma in terms of kinematic quantities. There is no equation which can exactly tell you that. So one has to resort to experiments basically to derive such relations. One does the experiment and then has experimental data, which then does numerical fitting to find out some formula for stress in terms of kinematic quantities. Okay, one makes some assumption that the material is isotropic, anisotropic, and further does some reduction. So basically, there is no equation which can tell you, or no physical law which can tell you that, okay, this is what the formula will be. But there are some, based on physics, the we do get some restrictions on what constitutive relation should look like. What property should constitutive relation satisfy? We do get such restrictions from physics. And so they are obtained through applying the following property. One is material objectivity. Okay, we'll discuss about this, what this is, or material frame indifference. Then we have what is called material symmetry. So we'll discuss each of these topics in detail in the following lectures. So these, objectivity or symmetry, which we don't know what it is till now, they will be used to have some restriction on how the constitutive relation should look like. But it can't tell you exactly the formula. It can only give you some restriction. Okay? And then, of course, the second law of thermodynamics also gives you some restriction. That inequality. So they give restriction on how constitutive relation should look like. So every constitutive relation must satisfy these three things. Okay. Any questions so far? See, we want to have a relationship between sigma and the kinematic quantities, which is information map y or temperature theta. But there is no equation which can exactly tell you how should they be, what that formula should be. But whatever formula it will be, that formula must satisfy these three properties. It must obey these three things. And that's going to put some restriction on that formula, okay? Okay, so let's now discuss about each of them one by one. And the first is, of course, material objectivity or frame indifference. So before that, I like to tell you that the deformation map, for example, this y hat of x comma t, or the velocity or acceleration corresponding to any deformation, aren't they all dependent on observer? I mean, you must have learned about that there is nothing like absolute velocity or absolute acceleration. They are all relative quantities. You measure velocity with respect to one frame, you get something. You measure it in a different frame, you get something else, right? So these are something which are dependent on frame, isn't it? But there could be quantities or physical quantities which should not depend on the frame. Can you think of one such quantity which should not be frame dependent? Irrespective of what frame you measure, that quantity should be same. Can you think of one such quantity? Density. Yeah, that is correct. Density is one such quantity. Anything else? Mass, yes. Temperature, very good. So there are quantities which are indeed frame independent. So such quantities are called objective quantities. Okay. Quantities which are frame independent are called objective quantities. Quantities, yeah. And you will see that your constitutive relations, when we talk about constitutive relation, it is much easier when we try to express the constitutive relation in terms of objective quantities. So their importance will come when we try to find out the formula for constitutive relations, for example. Okay. So this was just physics that, okay, quantities which are frame independent are objective quantities. But it's just sentence. We have to, come up with some mathematics to say that, okay, this is the quantity which will be frame independent, or this is the quantity which is not frame independent. So let's try to derive that mathematical thing, or talk about that mathematical thing. Okay. Now you see, suppose you have this body which is undergoing some motion. And you might be observing it from two different frames, or you can observe from so many frames. So frame 1, frame 2, frame 3, and each of the frames, with respect to each of the frames, when you measure the physical quantities like velocity, acceleration, they will come out to be different, but temperature should come out to be the same, right? Or density should always be coming out to be the same. And there can be many more quantities which will come out to be the same. But also notice that these frames um, can be related in some way. If you, for example, think of a frame denoted by a set of three vectors, if you think of a frame denoted by a set of three vectors, or let us say a set of three vectors, orthonormal vectors, set of three orthonormal vectors. Then each, here you have one set, then here you have another set, and here you have another set. But luckily, each of the triads, if they are orthonormal vectors, they can always be related through a rotation tensor. So for example, if you have here E1, E2, E3, and here you have E1 hat, E2 hat, E3 hat, and likewise here you have E1 tilde, E2 tilde, or E3 tilde, then they can be related. For example, EI hat will be equal to some rotation Q times EI, or EI tilde will be equal to some rotation R times EI. So you can relate them through rotation. Okay. And you can, I think, kind of see that when you measure quantities with respect to these frames. So when you, for example, measure a vector here, let's say you have a vector V, you measure it in this frame and you measure it in this partial frame. By measuring, I mean when you try to write down its components in the two different frames, then those components will be also related, isn't it? And they will be related through using this same Q. For example, a vector V, when you express it in the hat coordinate system, and you have the same vector V expressed in the without hat coordinate system, do you know how will they be related to each other? So I think this is something we have seen already, isn't it? So you will have then the rotation which relates the two coordinate system. This being expressed in the original coordinate system EI and with a transpose. Isn't it? And likewise, there is a relationship for tensors. Right? I think all of you will agree with me. So this is how you can find out how a vector, when you denote it in a coordinate system, in two different coordinate systems, and how then they will be related to each other. Okay, so, but coming back to discussing about measuring quantities in different frames. So you can see that the frames are kind of related through the rotation tensor. Okay, so let me say this statement. That observing a motion in different frames is equivalent to observing related motions in the same frame, but that related motion will be of this kind of relation. So we have, for example, y star equal to some rotation tensor qt into y of x comma t plus a constant t. Now such a relationship between y star and y, can you think of how are they related, this y star and y? Physically, how are they related? Mathematically, this is the thing, but physically, can you think of how are they related? The two motions. Yeah, you can think of CT as translation. And QT is rotation. Yeah. So basically, they are related through rigid body motion, related by rigid body motion. So whatever is the deformation in the motion y, you will have the same deformation in the motion y star. Will you agree with me? Y star and y will have same deformation, and they are just related through rigid body motion. And can you then say that density in y and density in y star, will they be same? Can you say that? Because they are related through rigid body motion. Likewise, density in temperature in y and temperature in y star will be same, isn't it? Right. So the material one is material framing difference. That means you're measuring from different frames and you should see the same thing. The other is you measure a quantity in related motion with respect to one single frame, and that related motion is through rigid body relation. And if you find the quantity to be the same, invariant in those related motions, then we say that that quantity is objective quantity. First case, observing same motion in different frames. And the second case is observing rigid body related motions in a single frame. So as far as finding out whether a physical quantity is objective or not, you can do either of the two exercises. Both will work. Okay. So in the following, we will use the second approach. Okay. We will now use second approach. I hope this is clear to everyone. Okay, so now comes the definition for objective quantities. And in the side, I will just draw those y and y stars. So we have this reference configuration of the body, and one is y, which might give a motion or a shape like this, and the other is y star, okay, which is the same shape but doesn't look like the same thing, but please think that it's the same thing. They are related through rigid body motion, related by rigid body motion. Okay. So objective is, there can be different kind of objective. It could be scalar, vector, or tensors. So when it is scalar, we'll say that suppose the quantity is beta, which could be temperature or density. So we'll say that beta, when measured for the motion y and at time t, it should be same as star when measured in motion y star and at time t. Okay. And for the vectors, suppose that in the motion y we have the vector b, and in motion y star we have the vector b star. Okay, then we'll say that it should be related in the following way: b star should be equal to qb. If b star turns out to be equal to qb, then we'll say that b star is a objective vector quantity. And for tensor, for example, if we have a for the motion a, for the motion y, and a star for the motion y star, then we'll say that if it has to be objective, then it must be related in the following way. So this is the definition for objective quantity. And why, for example, we are having such a relationship for vectors and tensors. And so that will be clear. For example, suppose that I'll do through a physical thing. Think of this motion y, and at a point here you have a plane, and there you have some traction t. Okay, and once this rigid motion happens, then at the same point, at the corresponding point and the corresponding plane, okay, I think it should be like, yeah, traction will be t star here, isn't it? Don't you think that t star will be equal to q times t? Because they are rotated by q, then t star will be equal to q times t. Do you agree? For the two motions which are related by rigid body motion, in one case you will find t, in the other case you will find t star, and they will be related in the following way. And this is for a physical quantity t, but for a general vector v, why we are enforcing that should mean it is objective. So suppose we have a vector field b here and a vector field b star. Okay, if you measure the components of B in a body fixed frame, okay, think of a body fixed frame here. And so here also you have the body fixed frame. So as the body rotates, the frame is also going to rotate. So it becomes E1 star, E2 star, and E3 star. So B dot EI, let us try to find out what is B dot EI and B star dot EI star. Okay. If the quantity is objective, if the vector is objective, then what it will mean is that this will then become QB dot with, and you see EI star and EI, how will they be related? Because it's a body fixed frame, and if there is a rotation Q, then EI star will be equal to Q times EI. So it becomes Q times EI, which is equal to B dot Q transpose Q EI, which is equal to B dot EI. So you see that for objective quantities, the components of the vector measured in the body fixed frame is the same. The components are invariant, right? If you define your objective quantity, objective vectors in this following way, then the component of the vector in the body fixed frame become invariant. And that is why we have related vectors as objective in that particular way. Similarly, similar thing goes for the tensors. So, for example, Aij is equal to A into Ej dot with Ei. Okay, and then A star Ij is equal to the tensor A star multiplied by Ej star dot with Ei star. And let us see how our Aij and Aij stars are related. If A is an objective tensor, then you can say that A star will be equal to Q into A into Q star, so Q transpose, and then EJ star, we know it's Q times EJ, and then dot with EI star, which is Q times EI. Okay, and you see that these two become identity, so we have Q A EJ dot with Q EI. Now bring it on the other side, and it becomes A EJ dot with Q transpose Q EI, which is A EJ dot with EI, is same as this. So again, what you see is that A star Ij is same as Aij if A star is objective. So this is the reason why we define for scalars, it is simply B equal to B star. For vectors, B star is equal to QB. And for a second order tensor, A star is equal to QA Q transpose. Okay. So that's the definition for objective scalars, objective vectors, or objective tensors. So you see that this definition, we are always measuring relative to one single frame. There's one single frame, but looking at related motions. Okay. Now let us try to see some of the quantities that we have already seen. Are they objective or not? Let us try to find that. For example, velocity. Is velocity objective? Okay, so what's the definition for velocity? So velocity is simply del y by del t, right? Keeping x fixed. Then what will be v star? V star will be del y star by del t, keeping x fixed. Now put y star in terms of y, so it is del t of q of t times y plus c of t, right? Keeping x fixed, which will be q dot into y plus q times y dot, which is v, plus c dot. So that's your v star. Now is v star equal to qv? It's not equal to qv because you see that it has extra terms. So that means v is not an objective quantity. Okay. So in your constitutive relation, v cannot figure as a independent term. The constitutive relation is something that should be frame independent. Similarly, you can think of acceleration also. Okay, and let us say something more. For example, we have deformation gradient f. So f is del y by del x, right? Or gradient of y with respect to x, Lagrangian gradient. What will be f star? That's del y star by del x. Put your y star, that's del qt of y plus ct with respect to x, and then what you get is qt into del y by del x, which is f, and then del c by del x is 0. So again, you see f is a second order tensor, but f star is equal to q times f. So again, it's not an objective quantity, right? So that means f is not an objective quantity. Okay. What else? Think of this v, for example, v. You know, f is equal to ru is equal to vr. So v is the, I forgot the name. It is left. It's not right. It's not the Cauchy green tensor. That's. Can someone tell me what we call v to be? So anyways, let us see how does v transform. So we just saw that f star is equal to q times f. So it is q into r into v, or q into v into r. Left stretch tensor. Okay, so it's left stretch tensor. Now this we can also write it as q into v into q transpose into q into r. Okay, and in this decomposition you notice that this is symmetric and positive definite. If v is positive definite and symmetric, then this is also symmetric positive definite, and this is a rotation tensor. So what this tells us is that r changes to qr, which is your r star here, and v changes to QVQ transpose, which is your V star over here. So what you notice is that V star is indeed QVQ transpose, and that's why V is an objective quantity. Okay. Likewise, you can see or you can think of what about U or more or several other measures. What about sigma, for example? Can someone think of what will sigma be? So for the traction, you notice that T star is indeed turning out to be Q times sigma. What do you think of sigma? Sorry, T star was indeed turning out to be Q times T. So it is objective. What about sigma? You will notice that sigma is also turning out to be objective. So maybe you try to work it out and show that sigma is objective. Okay. What about, for example, L, which is F dot F transpose? So F dot F transpose, that implies L star is then F star dot into F star transpose, and F star is Q times F whole dot into QF transpose. So QF dot is Q dot F plus QF dot, okay, multiplied with F transpose Q transpose, which is Q dot into F into okay, I think is this what is L? Yeah, there's F inverse, F dot F inverse. Sorry, it's not F transpose. Thanks. It is F inverse. So we get here inverse. So we have here inverse, and Q inverse is same as Q transpose. So we have here F inverse into Q transpose plus Q times F dot F inverse into Q transpose. Now, so this is equal to Q dot Q transpose plus Q times L into transpose. So notice that L star is not equal to QLQ transpose. It has this extra term. And this is actually skew symmetric tensor. It's skew symmetric. Okay, so what this means is that L is not objective. But what about the symmetric part of L star? So symmetric part of L star will then be equal to symmetric part of QLQ transpose. Okay, so that means D is objective, which is a symmetric part of L. So basically D star will be equal to QDQ transpose. But W, the spin tensor W star will then be equal to Q dot Q transpose plus W. So this implies W is not symmetric. Sorry, not objective. Okay, so I'm going to stop here and see you all in the next class. Okay, on Monday. We'll talk more about objectivity and how this is used in constitutive relation. Okay, thank you everyone.